Namaskara. In this session we continue our discussions on divide and conquer algorithms, and we are going to look into various subtle aspects of the algorithmic thinking associated with divide and conquer paradigm. A mindless application of a divide and conquer technique may not give an efficient solution. If you want to get a good mileage out of this technique, you should know how to apply it in a careful manner. So we are going to take a case study where we are going to examine various careful ways in which we can use this idea to arrive at a more efficient solution. Okay? So algorithmic thinking is at its best and very well explained through this example. Okay? We are going to solve the following problem: finding min and max. You are given an array A of n numbers. Let us consider integers. You are given n integers a1 to an, and you have to find the minimum and maximum of this. This is a very interesting problem. It has got some real world application. For instance, when you are zooming in and zooming out in windows, okay, let us say you have this and you have some points here, and when you expand they have to be properly spaced. Okay. In the smaller window it will be closer in proportionately. So how do you arrive at this proportion? So you may have a lot of points and you will get a bounding rectangle by finding the maximum and minimum of x and y coordinates, and that will define the bounding rectangle. And when you zoom out, the rectangle expands, the same set of points, but the rectangle expands and it shrinks. Okay. So in order to find out that, you have to find the maximum and minimum of x coordinate values, maximum and minimum of y coordinate values, and so on. So the algorithms behind this zooming in and zooming out and spacing will frequently use finding the maximum and minimum of n numbers. That is the reason why a lot of research has been done on this problem. And you have a very simple and naive algorithm, okay, a 2-pass algorithm. You are given an array, you want to find a maximum, a very simple maximum finding in an array with n minus 1 comparison for maximum, and again n minus 1 comparisons for minimum. You can find the maximum and minimum in 2n minus 2 comparisons. You have a very simple algorithm, and this is linear. Not only linear, and you can see that the constant is only 2. It is already a very good algorithm. But since this is going to be used so many times, so frequently, we would like to have a more efficient algorithm for this, right. So we would like to have the best possible algorithm. This is linear, theoretically this is very efficient, but now we are setting out to discover a more efficient solution than this with less number of comparisons. Okay. So we can try the divide and conquer approach. Since divide and conquer is leading to very efficient solutions, and historically it has made huge impact on variety of problems, matrix multiplication, Karastubas. So if you look at the impact of divide and conquer technique, it has already created several landmark results. So it is natural to try, can we have a divide and conquer algorithm for this? The answer is yes, we can have a very simple divide and conquer algorithm. It works as follows. Okay. Find the max and min of max and min of A 1 to floor n by 2, find max and min of the rest floor n by 2 plus 1 to n, call this as max 1 and min 1, call this as max 2 and min 2. In other words, you have split into two parts, you have their solutions max 1 and min 1, and on this part max 2 and min 2. For the first half of the array you have the max and min, for the second half of the array you have the max and min, max 1 min 1, max 2 and min 2. So how do you find the overall maximum? The overall maximum is larger than these two. So with one comparison you get max from this, minimum is smaller than these two, with one more comparison you find the minimum of the entire array. Therefore with two further comparisons you are able to solve the problem. Okay? So how do you find the max and min with two comparisons? Therefore the recurrence equation is T of n is T of floor n by 2 max and min in the first half, max and min in the second half, T of ceil n by 2, this is ceil n by 2, this is floor n by 2, and then 2 comparison plus 2. And when you have one element, right, when you have one element no comparison is needed. Therefore T of n equal to 0 when n equal to 1. So T of n is T of floor n by 2 plus T of ceil n by 2 plus 2. Look at the difference. Earlier in merge sort we had n minus 1 here, but now we have a constant. Okay. So this is a divide and conquer algorithm, and this is the complexity of the divide and conquer algorithm. So what is the our first divide and conquer algorithm is a very direct application, very similar to merge sort. Split the array into two parts, if n is greater than 1, split into two parts, combine them, combine their solutions, right, solve them and combine their solutions. The recurrence equation is T of n is T of floor n by 2 plus T of ceil n by 2 plus 2 if n is greater than 1, equal to 0 if n equal to 1. Unless I solve this in closed form, I can't compare with my naive solution. I have a 2-pass solution, that is 2n minus 2. Here I have a divide and conquer algorithm and I have to solve this in closed form. If I do not solve it in closed form, or if I get only a vague bound, I will not be able to compare with my 2n minus 2 figure. I already have a 2n minus 2 algorithm. What is the complexity of this method? So I have to solve this exactly. If I solve approximately and get some bound, that is not helpful. Let us say I prove that Tn is less than or equal to 7n. It says less than or equal to 7n. It could be any value. It could be 6n. It could be even n. This information is not useful, getting bound. For example, if I show that Tn is less than or equal to 7n, this is useless to compare with a 2n minus 2 algorithm. I have a 2n minus 2 algorithm, but to compare this I have to solve exactly. Okay. So, based on our experience, we define d of n equals t of n minus t of n minus 1, but here you have a constant. N minus 1 term also will have 2, n also will have 2. Therefore, you are not going to have any further term. Therefore, this is equal to, that constant will cancel, that will be equal to d of ceil n by 2, right. After the cancellation, you are not going to have any further terms. D of n is d of ceil n by 2. What is d of n? The difference. I know that d of n is same as d of n by 2, right. D of n is, so let us say what is d of 43. D of 43 is same as the d of ceil 43 by 2, which is equal to d of 22. D of 22 is same as d of 11. D of 11 is same as d of ceil 11 by 2, which is the d of 6. D of 6 is same as d of 3. D of 3 is same as d of 2. D of 2 is same as, okay, d of 2. I can go on, but d of 1 is not defined, only d of 2 is defined, because d of 2 is T2 minus T1. Okay. D of 2 is T2 minus T1. What is T2? T1 I know 0, T1 is 0. So, I know that d of 43 is d of 2. In fact, d of anything will be d of 2. Why? It keeps reducing like this, finally it will end up in 2, d of any value. Keep dividing by 2 and take the ceil. Okay. For example, d of 73. D of 73 is same as d of 70 is 37, which is same as d of 19, which is same as d of 10, which is same as d of 5, which is same as d of 3, which is same as d of 2. What is d of 2? D of 2 is t of 2 minus t of 1. This is defined. And what is t of 2? T of 2 is t of 1 plus t of 1 plus 2. T of 1 is 0, t of 1 is 0, therefore t of 2 is 2. Therefore, this is 2 minus 0, which is equal to 2. Therefore, d of n equal to 2 for all n greater than or equal to 2. D of n equal to 2 for all n greater than or equal to 2, because any value is d of 2. The difference is always 2. The difference is always 2. That is very interesting, right. Tn minus Tn. So, you can calculate hand calculate certain values and then see whether this is indeed the case. Okay. So, let us do the hand calculation. Here n equal to 1, t of n equal to 0. When n equal to 2, this is 2. What about T of 3? T of 3 you can see is T of floor 3 by 2 plus T of seal 3 by 2 plus 2. Floor 3 by 2 is 1, seal 3 by 2 is 2, T of 2 is 2. So 2 plus 2, 0 plus 2 plus 2, which is 4. Therefore, when n equal to 3, it will be 4. What is 4? T of 2 plus T of 2 plus 2, 2 plus 2 plus 2, which is 6. And what about 5? T of 2 plus T of 3 plus 2, this plus 2, 2 plus 4 plus 2, that will be 8. So you can see that it is 2, 4, 6, 8. The difference is always 2. The difference is always 2. That is what has been even formally proved. D of n is always, which you can, it is not only by numerical value, you can prove this D of n equal to D of seal n by 2. Assume that for all k less than n, D of k equal to 2. Strong induction hypothesis. How will you use it to prove D of n? When n is more than 2, like n equal to 3, this value will be smaller than n, right. N equal to 2 we have already taken. So, for any n greater than or equal to 3, n will be greater than seal n by 2. So, this is a value smaller than n. Therefore, D of n equal to 2 by induction hypothesis. Induction hypothesis is for all smaller value of n, it is 2. This is smaller value than n. Therefore, this is 2 by induction hypothesis. That shows that D of n is 2 for all n greater than or equal to 2. So, here T of n minus T of n minus 1 is 2. T of n minus 1 minus T of n minus 2 is also 2. In this way, T of 2 minus T of 1 is also 2. There are n minus 1 equations here. So, when you add all of them, the cancellation happens like this. T of 1 is 0, therefore, T of n is 2 plus 2 plus 2 n minus 1 times, that is 2 times n minus 1, that is equal to 2n minus 2. So, T of n, when I solve exactly, I get 2n minus 2. Okay. T of n is 2n minus 2. My naive algorithm is also 2n minus 2. Now, I said about divide and conquer, and then I have split into 2 parts and find the max and min here and max and min there combined, and I thought I will land up with a better solution. Unfortunately, it is not. The analysis clearly shows that its complexity is same as the one. Now, why should I use this algorithm? I have a very simple 2-pass algorithm. You can find a max in a for loop, you can find a min in another for loop without any recursive calls and splitting, combining, nothing, no complication. Simple 2-pass algorithm, I have 2n minus 2 algorithm. This is divide and conquer, but the analysis shows that this is same as that, right. This is why analysis is needed, and I have to solve it in closed form. If I do not solve it in closed form, and if I have only upper bound, I will not be able to compare. Now I am able to compare, I get the insight that this algorithm is no better than the one I have, and I will not prefer this because this has recursive calls and various other complications. The instruction count is same, number of comparisons is same, but the bookkeeping overhead is lot more here. So should I abandon divide and conquer algorithm? Not necessarily. Let us see how we can make things more efficient. Okay. So the first strategy is the following: check whether an early termination is possible. What is happening here is you are splitting the input into smaller and smaller and smaller part. The base case is 1. For example, if you take 12, 12 is split into 6 and 6. 6 is split into 3 and 3. This 6 is split into 3 and 3. This 3 is split into 1 and 2. 1 and 2. 1 and 2. 1 and 2. This 2 is split into 1 and 1. 1 and 1. 1 and 1. This is how the recursion tree looks like. If n is more than 1, you split. If n equal to 1, you return 0. If n is more than 1, you split. Therefore, the execution of the algorithm, if you look into the recursion tree, it will look like this. So you leaf will have the value and it will return. For example, this 1 or this 1 is going to return 0, this one will return 0, but you are going to compare the minimum and maximum, right? 2 comparison. At an internal node there will be 2, not return, I am sorry. It will do 0 comparison, this will do 0 comparison, it will return the min value, max value, because there is only one item, that is the maximum and that is the minimum. No comparison is needed. So with the 0 comparison, you come to here, mins are compared, max are compared, and min and max are returned. Here with 0 comparison you will return. Again min and max are compared, mins are compared, max are compared, min and max are returned. So in this way the leaves will have 0 cost, every internal node will have a cost 2, because that is where the comparison is done and values are returned. Final output is computed and you return it. In other words, this whole tree, this is for 12. You have to keep splitting until you get 1. So how many leaves you need? 1, 1, 1, 1, 1, 1, 1. 12 leaves. So in general, if I have n, it will have n leaves. It is a binary tree, right? Full binary tree, which means every internal node has got 2 children. Leaves of course will not have any. The key property of a full binary tree is that if it has n leaves, it will have n minus 1 internal nodes, and at each internal node you do 2 comparisons. It is a leaf, you do no comparison. At an internal node you do 2 comparisons and then return the value. So every internal node will, and there are n minus 1 internal nodes, 2 into n minus 1. In fact, this is the reason why our algorithm is taking 2n minus 2 comparisons. there are too many fragments and you have so many smaller subproblems. You have to combine the solutions of those subproblems, and many of them you try to bottom out a little earlier. Is there a scope to bottom out a little earlier in a more efficient way? So, if you look at the current recursive algorithm, how does it work on two inputs? Let us take A, B. How does it work on A, B? Split into A and B. What is the min and max of A? Min is A, max is also A. So, here you are giving min 1 and max 1, which is simply returning A and A. In min 1 A will be returned, max 1 A will be returned. Here min 2 B will be returned, max 2 B will be returned. That is how this algorithm works. When it is a base case, return the value. Okay. Other case you split. So, for n equal to 2 it will split, it will come to the base case in which 1. So, how do you find the overall minimum? Overall minimum is found out by comparing min 1 and min 2, that is comparing A with B, you find the overall minimum. How will you find the maximum? Again you are going to compare A and B and you are going to find the maximum. So, you are going to compare A and B and find the minimum. Again you are going to compare A and B and find two comparisons you are doing. Unnecessary, because when you have two elements, one comparison is enough to find both. So, if A is less than B or even less than or equal to B, min equal to A and max equal to B, else min equal to B and max equal to A. One comparison is enough. When you have this model, when you are recursing through, you are getting T of 2 equal to 2, not necessary. Why T of 2 equal to 2? When you have two elements, mins return A, max returns B, and again you are. So, when you bottom out at 2, you get T of 2 equal to 1. T of 2 equal to 1. This is going to give a significant saving. The algorithm, its analysis, everything will become a lot deeper. Okay? We will see the details of this in our next session. Thank you.